So, welcome. Thanks for making it. I see some familiar faces that I've had in 108 or as IAs or others. Some of you may not know me at all, but hi, I'm Jason. You can call me Jason, you can call me Dr. J, you can call me Professor Fleischer, I don't mind. If I don't call you by the name you prefer or I butcher a pronunciation, please let me know. You can correct me on the fly in person. If you feel embarrassed, you can email me later, whatever. Right? I will try to say people's names properly. I'll try to learn most of your names. What else? Obviously, welcome to machine learning. Who here is brand new in terms of machine learning? Never touched anything that seems machine learning-y? Anybody? Yeah, like a couple of people? Okay, at least half, realistically, right? I know that some of you have had something like COGS 108, which at least kind of starts the process, maybe COGS 109, or some other course, right? DSC something. Let me tell you about this class. This class, what we're trying to do is to give you a mix of theoretical basis, right? Math. Because in the end, why do we pick one machine learning algorithm or another? Usually the best reasons are not, oh, I got the high score with this one. Usually the best reason is, here's a theoretical basis why for this kind of problem, this is at least a good pick, okay? So I want you all to have a solid understanding of math. And yeah, this is maybe your first really hardcore math ML class, right? Certainly if you've had 108, we didn't do the math in that class. It's an opening, it's an introduction, right? I'm going to start you on a path to being happy with reading these kinds of math-heavy machine learning papers because that's what you got to do to be good at this game, all right? But that's not the only part of the game. It's not all just theory. We definitely want to give you a programming basis for actually getting stuff done, right? Maybe you've all gone on Kaggle or something else, and you've actually done machine learning things, and it's pretty obvious that you can get a lot done with modern software tools without quite understanding why it works or how it works. But hey, it's a software tool. You just, do this, do that. I got answers, okay? So that's why I want to give you the theory part, is so it's not just, I don't know how it works, but I definitely also want to give you that programming part so you can get stuff done. Okay? The last part of this course, from my standpoint, and in some ways the most important from my viewpoint, is thinking clearly about these kinds of problems. In 10 years, it'll be a new fancy algorithm that everybody's using. You'll have to pick that up. In 10 years, it might be a completely different software framework. You'll have to pick up something new. But thinking clearly about these kinds of model selection problems, about finding the best algorithm for the task, right? That should last you your lifetime. So thinking clearly about these kinds of problems really is what I consider the most important part of this class. Everybody cool? Any questions so far? I love interruptions. So let's talk about how to do this thing right. I'm going to try to run this. This is like only the second quarter for this, and I'm still refining it. But I want to run this course in a semi-flipped way. If you've had flipped courses before, you know what I'm talking about. I'm going to record short videos and put them out for you to watch on our YouTube playlist. Okay? These short videos should be hopefully less than 20 minutes, hopefully more like 15. I'm going to do them for just about every class period. There's going to be a video that's going to introduce you to the technical stuff so that when you come to class, We're going to spend some more time going over like the ins and outs, and I'll just assume that you have kind of the math basis that I'm going to introduce in the short videos. Okay? We're going to do hopefully some more interactive stuff. With some regularity, I'm going to try to at least once a week get a Jupyter notebook into a GitHub repo for you to load up and play with during class. So that's what I want. I want this lecture time to be interactive and worth your time to come. Otherwise, I know what I'm going to see at week 7 is 6 of you instead of 150 of you. Okay? So I want it to be worth your while to show up and not just watch the podcasts. But the podcasts are there. Okay? So if you're sick, please don't come to class. Okay? If you're like coughing, sneezing, don't come. If you have a fever, don't come. If you're just feeling a little bit ill, I'm okay if you come to class as long as you're wearing a mask. All right? That goes also for discussion labs and office hours and stuff like that. I have had to already kick students out of my office hours who were sneezing without masks. I know it's just 1%, but I have to say it for the 1%. Okay? More generally, besides the flipped nature of the course, you'll see there is a syllabus. It's on Canvas, right? There's you can go look at it. On that syllabus, you'll see that I link to 3 separate free textbooks. There are 3 classic textbooks that are all 3 in the public domain. So no cost to you, you just go ahead and take a look at them. I find it, especially when we go through the math, for me personally, seeing it in a textbook treatment is really helpful. I'm going to try to deliver the knowledge through my video thing and through here and live lecture, but sometimes it's just like sitting down and reading through a textbook treatment of the same thing can be really helpful. And these 3 different textbooks approach the same subjects, but they all do it from a slightly different direction. So one of them is very information theory oriented, another one's Bayesian theory oriented, and the other one's classic probability and statistics frequentist oriented. If you're not familiar with those 3 ideas, let me just be the first person to inform you that those are 3 radically different ways to see exactly the same thing that you're already familiar with from probability and stats. Okay? Different mathematical frameworks to understand the same process, probability and stats. Okay? We're going to do a little bit of that stuff. I will expose you to information theory. I'll expose you to Bayes' rule. But I don't really have the time to really push you through all the basics of that. But it is definitely something that I recommend that you maybe study further on your own at other courses or just by reading more of these texts. All right, for the programming bit, nothing beats trying stuff, right? Get into Jupyter Notebook, find some sample data, try to predict from it. Use the tools, play with them, do it over and over again, find online tutorials, go beyond what I'm going to be able to emphasize here, okay? The ones who are really going to get really cool projects are the ones who are going to fiddle and play beyond the assignments here. We're going to use CampusWire instead of Piazza this time around. Raise your hands if you've used CampusWire. Great, majority at least. If you haven't, it's at least prettier than Piazza. I think we're going to find the functionality better. If you're struggling, talk to people in person on CampusWire. If you're struggling with CampusWire, ask your friends and students sitting next to you, and we'll figure it out. Okay, same message I delivered in 108. I don't have the time or ability to deliver every single thing you might be interested in. This course does have a class project, like 108. It will be a group project. And maybe you want to do some special technique that I'm not going to cover. You're going to have to definitely have the ability to take what we teach you go read about some new algorithm that you want to try and learn the docs in scikit or PyTorch or whatever to do it, and then execute it on your own, because I just don't have the ability to teach you everything about machine learning, and certainly not everything you might want to try on your projects. Okay? So learning to be a learner on your own is definitely part of this course, just like 108. We want to give you the tools to succeed, and you should 100% ask us questions in office hours or on Campus Wire, but you will probably have to go beyond what we teach you. Any questions at this point? Okay. Let's talk about what you're all here for. You've probably seen this, right? It's probably why you're sitting here, or something like this. The idea that machine learning is big business. This quote, actually, it doesn't have a date, but it's circa 2007. So, as usual, Bill was right. We know now that there's just like 2/3 of Silicon Valley is, quote, AI, right? And half these companies are not really doing much in the way of AI. They're applying linear regression to some data to make a business. But that's okay. We're going to start talking about linear regression in this course, so I guess it's theoretically machine learning. Okay, so it has proved true. So let's ask ourselves, what even is it? Starting back with Arthur Samuel and the very first AI game bot, checkers bot, that was able to actually play against a good, classy human player. And there's a big accomplishment in 1959 where you know what those computers look like, right? So the idea is that we want the computer to learn for itself without being explicitly programmed, without having to lay out a full set of if-then rules for how to play a checkers game. All right? So let's do something maybe a little bit more useful as an exercise, which is to realize that any kind of machine learning AI program, we can break down the problem into 3 bits. Right? We want the program to learn from some set of experiences. We're going to notate the experiences as E. So this is your first math notation. All right? It's trying to solve this task. We're going to notate that as T. And how do we know it's doing good? Well, we have to have a performance metric for the task. That's P. So P is a measure of task performance. We give a system E, and it gets better at performance with that experience, right? Before we give it a test, it has a certain level of performance. After we give it some experience, it's now better than it was before. Okay, let's actually take a look at a classic in the machine learning literature. Who knows what this data set is? MNIST, M-N-I-S-T, right? Who knows the story behind it? Do you know the story? I saw your hand went up. Yeah.
It was a data set for compensation. It was for the original would be for the mailing.
Yeah, you got it. So the U.S. Post Service, back when I was a kid, was done by hands. Like, somebody got the letter, looked at it, stuck it in the right mail carrier's bag, and the mail carrier took it to the place. Now, there's robots, right? It's just these giant sorting machines that you zips through, it OCRs your handwriting, and then it has to learn, people's bad handwriting and know when you have a 7 or a 1, which can be pretty confusable. So this is the original data set for the first contest of machine learning to solve this problem for the post office. So this is an old data set, very low resolution. Each one of the numbers is 16 pixels by 16 pixels in the original MNIST. The modern versions are 64 by 64. And we just hard threshold, like when it's dark enough, it just goes to 1, and when it's not dark enough, it stays at a 0. So it throws away a bunch of details about the image, right? Let's talk about this baby. So what's our task? Our task is we want to recognize the digits. See, look at my handwriting. Right? That's supposed to be a 9. Okay. We want to recognize 0 through 9. What's a good performance metric? Somebody help me out here. How could we measure performance at this task? Yeah. How many gets right? So, like, you want to do like raw number right, percent right?
The ratio of right ones to wrong.
Okay. A ratio of right to wrong. So our performance metric is when we're perfectly correct, we get 0 wrong. What happens now?
I meant right over total.
Sorry?
Total?
Oh, right over total right. Okay. Number correct over number incorrect. Or number total, sorry. All right, Mondays. Okay, so we've got a ratio which is going to approach 1 when we're perfect, and is going to approach 0 when we're terrible. Okay? So that's totally reasonable. There's a performance metric. Let me point out it's not the only choice, but it definitely measures our performance on this task. Who could come up with a different way to measure performance? Yeah?
I mean, I guess it's similar-ish, but like false positive and false negative.
False positives, false negatives. So, right, like let's look at this. We're trying to recognize ones. Okay? What if we accidentally call some 7s, which, look pretty similar to 1s? False positive, call them 1s, right? Or false negatives. What if there's some 1s that have a little bit of a 7-ness to them, and we say those are 7s instead of 1s? So false positives and false negatives are a different way to look at this, and it's a more fine-grained way than the ratio of correct, because it shows us not just, hey, how good are we overall, but systematically what kinds of errors are we usually making. So if you remember from stats class or from 108, false positives and false negatives are different kinds of errors. They're both going to show up as an error here. They're going to be not right in this metric. But they're different kinds of errors. So that's what I want to get at. I don't want to go deep into this because we're going to get deep into this in like week 4. But there's more than one way to measure performance, and they show you a different lens on your performance. Which one's right? I don't know. What do you care about? Right? So we're going to talk a lot about how metrics are picked based upon what we care about. All right, what does experience look like? Well, for the MNIST data set, oh God, I can't even remember. Is it something like 30-some thousand, 60, 37,000? It's in my head. Anybody worked with it more recently than me? Yeah? Is it 60,000? Okay, so there's, say, 60,000 of these beasts. And roughly speaking, it's about even between the 0s and 9s, right? Everything's about 1/10, so it's about 6,000 per. So here's what we typically do in machine learning. We don't typically use all of our data to train on. Who knows why? Why would we not want to use all the data? So.
You train the model on usually 70% of data. Then you validate your data. Usually validation is 10%. And then you test your data. You test your model on 30%. So basically, if you expose your test data to your model, then it's overfitting because it basically trains. for that specific data set, and then we don't really know if it's going to perform good on the novel.
You got it. Okay. So let me rebroadcast for the podcast and kind of integrate all that information for people. Whatever your machine learning systems are way too powerful, okay? They can memorize answers in the data you give them. But we don't generally want it to memorize the training data. Usually we want it to generalize. We don't want it to just spit out the answer in a tiny little chunk of data we happen to train it on, because that data's got random noise in it. And if we're memorizing that data, we're memorizing random noise. So any chunk of data that a machine learning algorithm sees, it's probably overfit on that data. It probably has learned not just the signal, not just the thing we want it to learn, it's probably learned aspects of the random noise that's present in the data. But ideally, we want it to generalize to new, similar data and do really well on it. So here's how we deal with that. We always take our data set, we use part of our data set to train on, and we use the rest, the stuff we didn't train on, to guesstimate how well we're going to generalize into the future. And there's a lot of different ways to do that. Sorry, I forgot your name. I never got your name. Anna. So Anna told us one particular way, which is to split the data 3 ways, some for training, some for model validation, and some for testing. That is a typical way to do it, but it's not the only way to do it. We're going to talk about a lot of ways in which we use our data, part of it for training, the rest of it for figuring out how well we're going to do in the future. Okay? So we take our data, we split it into a training set, and in this case, I'm just going to say a test set, and maybe something like you suggested, Anna, 70% and 30%. We train on that 70, and then we check our performance metric on that test set. And that gives us, however good we are on that test set, we've never seen that data before, that's our estimate of how well we're going to do in the future on this same problem. Okay? All right. We're just about on time. So we've got a little bit of time to play. What's your favorite machine learning application? Anybody got one? I haven't been over on this side of the class yet.
BirdNet.
Sorry?
BirdNet, for recognizing bird sounds.
BirdNet. Recognizing bird sounds. That's really cool. All right. Any other cool apps? Or Anna? Image generation, like DALL-E or, right? So, yeah?
Recognizing breast cancer before
Recognizing, sorry, I just didn't process.
breast cancer in women.
Oh, breast cancer, yeah. So like various kinds of radiology, for instance, like breast cancer detection, right? So there's a whole huge world of medical imaging. Roughly speaking, doctors are expensive, right? So if you can do some pre-screening before the radiologist sees it, that can be really helpful. Anything over on this side? Up there.
The glorious ChatGPT.
Of course. I was waiting for it. Thank you. ChatGPT or GPT-4 nowadays, but you have to pay for GPT-4, I think. Yeah? Speech to text on your phone right now, right? This, my friends, when I was in grad school, was considered an unsolvable problem, and now you have it in your pocket. Yeah?
Why was it unsolvable?
Well, so with images, like we had an idea very long time ago on how to transform images to make them invariant, right? The idea that you should be able to recognize the stupid iPad, whether you see it like this or like this or like this or over here instead. So we had math to deal with that and to pre-process images so that we could set them up in these invariant feature space to make it easier for the machine learning. But we didn't really know how to do that with speech. It's surprisingly hard. If you've ever worked with waveforms, maybe you've seen this. And then, well, two things happened. One is we got better at the math and we learned ways to do that to make it at least plausible. And then big neural networks came along. And as we'll learn about when we get to big neural networks, half of what they're doing is they're creating their own features in their middle layers. So instead of us having to engineer a set of invariant features, the neural network is finding it for itself. So those two things both happen to make it usable nowadays. Okay, great. I think we all kind of know. Nowadays, when I teach an ML class, it's very different than like 10 years ago when I had to really explain ML. I think we all have a good experience of what ML is, if maybe not the tech details. So let's talk turkey then. Supervised learning, it's what we're doing in this class. What does that mean? It means that we have labeled training data. It means somebody has come through and produced for a data set the right answers. And that lets us train an algorithm knowing what the right answer should be and using the right answer to adjust the algorithm to be more right in the future. Okay? Labeled training data, direct feedback to modify whatever we're modifying in this given algorithm to learn better. You can use this for all kinds of things. You can use it to predict continuous variables like a regression. You can use it to classify different bird songs, right? BirdNet. You can use that same thing to fit a model. We'll talk about that in a minute. So that's us, COGS 1118A. Anybody taken B already? One? Only one? Two. Okay. Sorry, my peripheral vision's terrible. Okay. So B is unsupervised learning. There is no labeled data. In unsupervised learning, roughly speaking, what we're looking at are algorithms that have their own idea of the structure of the problem. And if what you're looking at is like a principal components analysis that maybe you're familiar with from 108, right? What it's doing is it's assuming the structure of the problem is that it's trying to discover is the variables that are explain most of the variability in the data. And that becomes the first principal component, right? Or to do my PCA physical demo, if you look at my iPad, this direction does not explain much of the data. This direction explains a lot more of the data, right? We're looking for where most of the variability of the data points lies. Okay, so that's unsupervised. There's no labels, there's no right answers. It's just using structure assumptions to find ways to look at the data and say, these two things are more similar than this thing and that one. Okay, reinforcement learning. If you have a problem, like solving a maze, or choosing your path through college, where you don't know whether you've done it well until you're basically done, that's reinforcement learning. The problem is this. We have this delayed signal of, did we do it right or wrong? Did we find the end of the maze, or did we just get lost and never come out? And we only know that answer at the end of the process of going left, right, left, right, left, left, left. And once we find the goal, we have to assign credit to the things we did 200 steps ago to get here. We have to know what 200 steps ago contributed to the solution versus 100 steps ago versus 1 step ago. That's reinforcement learning. It's a very important kind of learning. It is super, super hot right now in the machine learning world, but it's been around for decades. So COGS 182 for that stuff, or other courses in CS, et cetera. Okay, neural networks. We're going to talk a little bit about them, but this course only gets to them at the very back end, and we don't go that deep into deep networks. That's my joke for the day. So you want more deep networks, go check out 181. Genetic algorithms. They were super hot when I was in grad school. They're not so much now. But the idea is that it turns out most AI is kind of fundamentally search. Well, one thing that also is search is, animals having sex with each other and producing better and better offspring at staying alive. So taking natural selection and turning it into program selection using the ideas of having a bunch of solutions competing with each other to be the best solution. Okay. Anyway, yeah.
Are all of these, maybe with the exception of genetic algorithms, based on our understanding of the brain?
Ooh, good question. Yeah-ish. So as I'll talk about, neural networks are definitely brain-inspired, right? It's in the name. Reinforcement learning absolutely comes from psychology and things like that are proposed learning rules for how animals learn. There was a time at which this stuff here was seen as brain-ish, like the 40s. Feedback control systems were once seen as brain models. Anybody have feedback control systems? No, I'm the only engineer in here? Okay, right? But we definitely, you could say that a lot of this stuff was inspired by biology at one point or another. Okay. Cool, so I think I kind of got a little slow there, but. So supervised and unsupervised. I think we kind of covered this already. But the idea is, in this class, we're going to have the right answer, and we can use that right answer to make our algorithm better. In unsupervised learning, we're just extracting statistical regularity or some other form of regularity and seeing that all the apples are more similar to each other than the bananas, right? So we've got, in supervised learning, we've got the correct answer, which can be used to drive the prediction, or we just let it extract statistical regularity in an unsupervised way. Okay, I'm here to tell you that modernly this is a false dichotomy. Guess what deep neural networks do? Both at once. Okay? But we're going to talk about them in the basic introductory courses if they're separate things that can't be mixed. So this is what a modern deep neural network does. First, it gets trained in an unsupervised way, extracting statistical regularity without any kind of labels. And then after it's done that for a long time, then we take this network, which has extracted statistical regularity in an unsupervised way, forming these features that are useful, and then we try to train it to do a particular labeling task in a supervised way. And because we've let it extract unsupervised information itself, we can train it to do the particular task we want much more quickly. Who's used ChatGPT? How many times do you have to tell ChatGPT something? Once, right? It knows what you're talking about from a single presentation. Neural networks that haven't extracted the statistical regularity of English would need to be trained on your intention a lot more than once to give you a good answer. Okay? That's this so-called zero-shot learning. That's the name of the game with current neural networks. Okay. So, regression versus classification. All my COGS 108 people say, hey. Hey, come on. I know. There's not enough coffee in this room. So regression is we have two continuous variables, right? Like the pitch of an animal sound and its weight. and we're finding some sort of relationship between two continuous variables. That means it's in the set of reals, right? I'm going to bring some notation in here. So our inputs and our outputs are real numbers. Classification, our inputs may be the same thing, right? It's still going to be sound and weight, but our output is now a discrete category, one of a small number of things, okay? So our category here is maybe birds and not birds. So everything on this side of the line is a bird. Everything over here is not a bird. This decision boundary is a line. This line of regression is a line. It turns out the math behind both of these is just a linear equation, right? It's the same y is equal to mx plus b that you've been learning since middle school. It is not hard math. The only difference is how we're using that line, right? We're just saying, in this case, this line is the relationship, and in the case of the decision boundary, it just means that everything over here is a bird. So we're just going to use the math differently. And that's why I've got the false dichotomy on this too, because really it's the same math. It's just how we're using it. Okay, so regression. Regression, like I said, the output y is a real number, right? So with this kind of stuff, that means that you can compare things, right? y1 can be bigger than y2. We can make that comparison. For categories, that's not the case. There's no way in which bird is greater than not a bird, all right? No way in which blue is greater than green. Those sorts of relationships don't exist in categorization. Okay, so in regression, we got it easy. We just use the y value. It's a number. Really easy to understand. These are called ordinal. Classification, things are not ordinal. There is no way in which bird is better than not bird. Okay? But we use numbers to do the math. And so even though the use of +1 and -1, where +1 is going to be birds and -1 is going to be not birds, that kind of implies to you ordinality, okay? But that's just mathematical convenience. There's no way in which birds are actually bigger, okay? So it's important to realize that these labels, this ground truth, is non-ordinal, and we need to make sure we don't make mistakes assuming ordinality. We can make math mistakes by using this y output as if it is ordinal, okay? That will make more sense to you later when I show you examples of that, but for right now, just trust me. Even though these values are +1 or -1, or sometimes we will occasionally use +1 and 0, again, for math convenience is why we do stuff like this. These are not actually ordinal. Okay. So maybe we should start by asking the expert on machine learning. Let Google autocomplete tell us what machine learning is. Right? Machine learning is just, all these things. But I'm going to tell you that, in fact, what machine learning is it's just picking an appropriate model and then minimizing some loss function. And that leads to all of these things, to regression, to statistics, to if statements, to curve fitting. They can all be recast as this same process. All right, so let's take a look at machine learning is just regression. So what if we have what you're used to? Y is equal to mx plus b. I'm going to, instead of calling it M, I'm going to call it W, because what I want to set up, and we're going to go into this math more deeply in week 2, is the idea that we can use multiple variables, not just one variable, not just x, but x1, x2, x3, x4, x5, a lot of predictors, and come up with a target y, okay? So this is matrix notation. It is definitely Wednesday, next lecture, when we're going to remind everybody how linear algebra works, right? But that's what we're doing there, linear algebra. So we have a bunch of x's. So this is using linear regression, linear in the w's, linear in the parameters, okay, to fit, in this case, a nonlinear line. But we're getting that nonlinear line because we're fitting x squared and x cubed and x to the m power here. Okay? It's using linear regression to fit a nonlinear thing. So this is curve fitting, it's regression, and yet this technique is the basis of lots of stuff that goes on in, quote, machine learning circles, right? Even that big, deep neural network that's trying to predict the stock market, its output layer is going to look exactly like this, okay? The big neural network part is just finding the features for you. All right. Critically, I want you to start to think of this parameter W. This parameter W defines the model, right? That parameter W says, oh, the important terms are the x and the x squared, and the rest of those, the x cubed and the x fourth, those parameters are mostly zeros, okay? They're not very important in this prediction. So that's the model. Those weights in the regression, they are the model that's being fit. It's telling you what's important in predicting this problem accurately. Does that make sense to people? So the weights, the W term, this is the model that we are fitting. All right. Maybe you saw the bit about it's just if statements. Well, that's 100% very doable. This is the way a lot of machine learning algorithms like decision trees work. So if a particular variable is over a threshold and another variable is under a threshold, then this might be spam email. And if we have the opposite relationship, it's probably actually email sent to me by a friend and not a spammer. Okay, so in this case, these are frequencies of words occurring in an email. And if it uses your actual name, then it's probably more likely to be actually your email from a person than if it says, hey, you, or, you know, my dear, I don't remember how the Nigerian spams start. It's always my dear something, right? So that's the basis of the original spam filters from 25, 30 years ago. And it's still used today. Okay, so if software ate the world, models will run it, says some journalists who are kind of important in how Silicon Valley ended up creating itself. So again, the software industry is huge. But what's important to the software industry now are the models that are being formed to make money with, right? All these, quote, AI companies, what they've got is they've got access to a bunch of data on a business process, and they're fitting a regression model on it, and they're using that regression model to make predictions that make them money. Okay, so in the end, it's the form of the model which really, really is the important thing. What are those W's? What are the weights? And how do those weights not just impact some company's bottom line, but everybody else in the world? Right? If your software company is really, really good at making money, making payday loans are not very good for the people that take them. How about the people that get rejected from them? Is there any systematic bias on race or gender or something on this algorithm? So we'll talk about that stuff as well. But in the end, it's the models that make up the worth of a machine learning system. And it's important what they are, how they're used, and whether they have any systematic bias in them. Okay, so we have 5 minutes, a little bit less. Let's talk about what goes wrong. Data. Data is what goes wrong, okay? I mean, we can just stop there. Increasingly, what we're realizing in machine learning, especially now with modern techniques, that as long as we have the data, we can get beautiful answers. But oftentimes, the hard part is getting any data on the problem, or that the data we get is biased in ways that make our answers terrible, or the data we've got are not nearly enough, right? They're non-representative of the problem, they're insufficient in their quality, something. So because we know about overfitting, when we get data, we need to be careful that our answers we're giving for the future are not overfit, that we're accurately estimating performance. Medical imaging came up, right? COVID. I cannot tell you there were within a year, there were 200 papers on people that were going to use machine learning algorithms to use your microphone on your phone to diagnose whether you had COVID by the sound of your cough. I'm not joking, there were more than one paper on that. How many ever went to production? Overfitting, even though they had good results in the paper. Okay? Okay, so we're going to talk a lot about how to find out what kind of model is good and do it in ways where you're not tricking yourself into thinking, oh, here's my high score, it's a great model, and then when you get new data next Tuesday from the same process, suddenly you're performing really badly on the new data, that you're not overfit to it. So this kind of model selection and hyperparameter tuning, that's where we really have to be careful not to fool ourselves. And we also already talked about this, right? How do we even measure performance? What's the metric that we're doing? So in the end, what is machine learning? We need to develop your thinking skills, your intuition skills. We need to develop your math skills. We need to develop your coding skills. And in the middle, we got this beautiful machine learning algorithms. But in the end, if you give them garbage data, it does not matter how good the rest of it is, right? It's garbage in, garbage out situation. So, so here we are. We've got 2 minutes. Just please don't run away yet, okay? What we're going to talk about over the course of the quarter is the small-scale art of machine learning, right? What we do here at the academic level, where we get the data and we learn about it and we curate it and we clean it, just like in COGS 108. We explore it so that we understand what kinds of algorithms might be appropriate using a little bit of EDA. We transform the data to make it easier for our machine learning algorithms, like the invariant object recognition stuff. And then we split the data up, train, test, try not to overfit, use cross-validation, we do the machine learning bit, and we evaluate and interpret our results. That's what we're going to do this quarter. Let me just point you at the fact that out in the non-academic world, machine learning works at much bigger scale. We're not going to talk about things like how to maintain a Google-sized machine learning pipeline where you are continually reevaluating your model and keeping track of which version of the model is in production and which one's in development and what data in this continually changing data fire hose was used to train which model. This kind of large-scale production ML engineering stuff is fascinating. It is also an amazing skill set to have, but we don't teach it in this course, okay? So I do want to make you aware of the fact that you should take a look at this diagram and maybe at the end of the quarter, come back and look at it, and it'll probably make a little bit more sense to you and may give you some ideas of your next steps. Okay, that's it for today. Thank you so much. See you on Wednesday. I will put out a video tonight or tomorrow morning onto the YouTube channel, linked in the syllabus. Hey.
I just had a really quick question. I haven't taken COGS 108
Yeah.
because it's just not, like, it's filled up so quick
I
this
know.
quarter as well. But I'm wondering how much this class like requires knowledge or something, because I tried easy